Hello, my name is Elaine Hale. I'm a senior research engineer at NREL focused on demand and supply side interactions in future power systems. Today I'll be presenting material as part of the Enhanced Load Modeling and Forecasting online course. In this module, before giving an overview of the load modeling work I lead in the U.S. context, I will give a general categorization of long-term load modeling and forecasting approaches and place both my work and some well-known international models within that framework. Then, as part of the deep dive and in the conclusions, in addition to describing my work, I'll try to point out here and there where there's some first steps that grid planners can take to improve demand representation in their grid planning processes, even if they haven't thought that much about demand in the past. A key way we distinguish between different kinds of load models and forecasts are by qualitatively describing them as either top-down or bottom-up. These aren't hard and fast categories, but in general, when we say something is top-down, it relies a lot on historical data and some basic trends we might see in that data to describe or forecast electrical load. If we say that an approach is more bottom-up, what we mean is that we've sliced up electrical load into smaller pieces, either by sector or geographically or temporally, and we're using some finer scale measurements, and we might also be representing more of the physics involved or more details about the economics involved to put together a picture of electrical load that we've built up in detail, which then allows us to dig down and try to see where our understanding seems to be good and where we maybe need more refinement or don't understand some key relationships. A lot of times load models or forecasts include both types of components. The kind of high-level historical data that we use in top-down load modeling is generally an important reference point, even if we have bottom-up aspects of our work. Even if we're taking largely a top-down approach, we might take a bottom-up approach just for pieces of the load that we're trying to understand in more detail and basically combine those together to capture what we think the key drivers of change might be, or what just the key aspects of the load are that we want to understand better. So if we dive into this a little bit deeper, we can think about top-down and bottom-up approaches that we've seen folks take for both load modeling and load forecasting. So first, what is the difference between load modeling and load forecasting? I think of this as more of a perspective or an orientation we're taking when we're thinking about electrical load. If we're taking more of a load modeling perspective, then what we're really focused on is describing the load that we see, even if that load's historic or current or how we think load might look in the future. If we're doing the load modeling aspect of that, what we're really trying to do is just describe the load in more detail, how it varies in time and space, and what are its biggest correlates, how does it change, or how does it depend on weather or various economic assumptions. If we're taking a load forecasting perspective, then we are really focused on that question of how load changes through time, and we're probably sitting at a specific point in time and we're wondering how the electrical load might change over the next 5, 10, 20 years. So depending on what perspective we have, the top-down versus bottom-up approaches might look a little bit different. If we're doing top-down load modeling, then we're really focused on what does historic load look like, and can we relate some high-level variables like population, economic conditions, or weather, can we relate those to what the load quantity and shape looks like? If we're doing load forecasting with a top-down perspective, then we might be looking at econometric models that relate energy use to things like GDP or industrial output, as well as energy intensities. That would be a very high-level approach, but there are other, depending on the data you have, you might have other sorts of econometric kinds of models that you might call a top-down load forecasting model. If we're doing bottom-up load modeling, then we're trying to develop a more built-up, statistically representative, physically accurate picture of how energy demand actually appears, kind of maybe starting at that household or that building level, and then adding up a bunch of those to create an overall picture of load. These can vary a lot, and we'll talk a little bit later about work that I do coordinating a lot of engineering models of load into an overall picture of electrical demand. If we want to do a bottom-up load forecasting approach, then there's a number of different things we might get into there. Generally, you need to have a better understanding of how an economy's structure results in energy demands. You can start with service demands, like how much lighting or heating or cooling is demanded by a household or a commercial building, how many vehicle miles are traveled per person. We can kind of build up an overall picture of these service demands for a given region, and then use, for instance, a bottom-up load model to turn those service demands into actual energy demands, both electricity and other fuels like natural gas or gasoline. Basically, as we go to more bottom-up approaches for either the forecasting piece or the load modeling piece, the data demands and the computing demands often increase. Again, there's no hard and fast rules here, but I think it's fair to say that depending on what quadrant of this diagram we're in, we're more likely to be using certain kinds of mathematical or modeling approaches. If I'm looking at top-down load modeling, I'm probably using various statistics, maybe some time series analysis to understand load. If I'm doing top-down load forecasting, that's more of an econometric model kind of realm. If I'm doing bottom-up load modeling, then I'm often using engineering models. And if I want to do bottom-up load forecasting, then I'm going to need to start to get into a few different kinds of questions. I might be looking at equilibrium or partial equilibrium economic models. I'm almost certainly need to look into questions of technology adoption, how people make the decisions to adopt one technology over another. So these are just the kinds of models you typically end up using. And like I said before, there's a lot of ways to mix and match these approaches. So some examples of intermediate approaches are you could do mostly top-down load modeling, but do some engineering modeling of key end uses to understand those better, especially if they're a large part of your demand or if you expect those to change a lot in the future. So you could combine that kind of bottom-up modeling with the top-down load modeling. It's certainly helpful if you're doing bottom-up load modeling to calibrate those models against top-down metrics. So that's a combination of a sort. And you might also do bottom-up load modeling of top-down economic forecasting results. That's another combination that we've done in our work. Because my work is mostly focused on bottom-up load modeling, another key way that I think about load models is with regard to how resolved they are on these three different dimensions of geography, time, and sector level detail. All three of these dimensions we can think about as having both an extent and a resolution, where the extent is how much space, time, or sectors of the economy are you covering, and resolution is how at what level are each of your data points. So if I have a highly resolved model on the geographic dimension, I might have a data point for every customer. And if I have a medium level resolution model with regards to time, maybe I have hourly data for a few representative days of the year. Basically, in all these dimensions, we have choices in both extent and resolution. And what we were talking about previously with bottom-up versus top-down, that really applies to this sectoral dimension. How much are we breaking down load into its constituent parts? But when we're thinking about data needed and effort needed to do load modeling or load forecasting, how resolved we want to be on the geographic and the temporal scales can be important as well. One of the things we've found while doing grid integration modeling at NREL that's really important when we're trying to understand how much renewable energy we can integrate into a grid system is being really careful about having time synchronous data for load, wind, and solar. And so a lot of our early grid integration studies, and really a lot of grid integration studies that still happen today, often focus on using historical hourly load data from a specific weather year that's aligned with the same weather year that's modeled in the wind and solar data. And we really do recommend this as a good starting point for getting a more detailed understanding of load and how it interacts with renewable resources. So that really corresponds to what's hopefully a manageable level of data. You want to get your historic load shapes measured at the hourly scale, but it can be all the load altogether, including losses you see on your system. You know, just what was the hourly load that your system served in the past. And then what we've done is scaled those historic load data up using projections of load growth. So that's kind of economic growth combined with a notion of the energy intensity of that economic growth. If we combine those things together, then we can get a first order idea of what load will look like in the future in a way that is going to let us see the correlations between load and renewable resource. So for example, this is a load curve for a particular region, and in typical planning or historical planning processes, you know, maybe we would do planning just by looking at the annual electricity consumption and the peak electricity consumption. That would tell us how much capacity we need to have and approximately how much fuel we would need to use to generate the electricity. A next step after that would be to look at a load duration curve and to see kind of how much base load there is, intermediate load, and then peak load. But as I was just saying, when we start to think about integrating in more renewable energy sources, then it becomes more important to get a feel for this whole load curve as it flows through time, both its diurnal aspects and its seasonal aspects. For instance, you can see on this curve that there is more demand in the summertime, and understanding how that higher summertime demand does or doesn't line up with renewable resources can be really important. We also see that shoulder seasons, those fall and spring times when the weather is mild, can be challenging in some interesting ways when we have lots of wind and solar. But basically, you know, if you don't have hourly load data, then you're not going to be able to see some of those patterns or feel confident in them. And so that's really where we recommend folks start, is by using some historical hourly load data, time synchronized with wind and solar. All right, now kind of turning to what some different kinds of load models look like. This is a figure I pulled together to get a feel for how our load modeling project, which is called the Demand Side Grid Model, or DS Grid, how it kind of compared along these extent and resolution axes that we talked about before, how it compared to other load modeling efforts in the United States. And so you can see kind of a variety of different models and a variety of different approaches are kind of reflected in where these models end up getting placed on these diagrams. I won't do a big deep dive here though, because this is pretty US centric, but if we turn to some international models and take a look at what their characteristics are in terms of being top-down, bottom-up, or more of a model or a forecast, and also maybe how resolved they are or could be, we can start with the LEAP model. So the LEAP model, the way that it looks at energy demand is really a great example of a top-down econometric load projection. Starting from a certain level of energy demand, the future energy demand is projected based on population, macroeconomic indicators, and energy intensities. MADE 2 takes a similar approach, but with a lot more detail. So I'd kind of call it an intermediate model. It has a econometric flavor to it, but it does layer on the ability to capture more sectoral detail, demand-side technology options, and is also able to provide some load shape information. The times family of models is quite different. It's not an accounting kind of model like LEAP and MADE 2 are. It's a partial equilibrium economic model that has a flexible level of detail, which I think is what's resulted in there being sort of a whole bunch of different models built on the times platform. So the temporal resolution is configurable, but in all cases, the demand representation in times has to be kind of set from a reference point perspective with exogenous inputs of energy service demands and also population and macroeconomic driver inputs. Once you've provided those reference points, the times model is able to project changes from that reference point based on elasticities and various constraints and feedbacks in the model. So it can kind of result in different load projections, but you do have to tee it up first with sort of a reference point that it's working around. Then Ball-Morrell and Energy Plan are similar to each other, but really have a different focus from these other models. Neither of them really projects demand in any way. Energy demands or energy service demands are exogenous inputs to these models, but what they are able to do is model the trade-offs between different energy sources. So for example, these models can come to different decisions about how to satisfy a heating demand, whether with direct combustion, a heat pump, a district heating source, or a combined heat and power plant. What decision these models would come to would depend on the other model inputs. The load modeling effort that I lead is called the Demand Side Grid Model, or DS Grid for short. The overall approach is to leverage the energy modeling work that has been done for the different sectors over the last few decades. But what we're doing differently is we're really asking those sectoral models to provide data that's suitable for grid integration modeling. That typically involves asking for data at a higher level of geographic and temporal resolution than these sector energy modelers maybe have needed to provide in the past. The main reasons that we've undertaken this effort is that we want to capture how technological change could impact future load shapes. And we also want to provide a solid basis for analyzing how operating loads more flexibly might enable more wind and solar generation, as well as provide other grid benefits. Another benefit of taking this kind of approach is that we can help the sector modelers understand any trade-offs that they might have in what technologies get used to provide different energy services based on what grid energy looks like and how it might change in the future. So going back to our load modeling and forecasting categories, the DS grid efforts thus far have really been really focused on bottom-up load modeling, with a lot of emphasis on technological detail, physical realism, and high-resolution data. What we're starting to do now is look more deeply at load forecasting. We created 3 load projections for a project that's almost done now for the city of Los Angeles. And in that case, we're really doing combining kind of a top-down load forecasting approach with our detailed bottom-up modeling. But now that that project is wrapping up, we have an opportunity to look more closely at how we want to create load projections going forward in a national context, and potentially needing to respond to a variety of different kinds of research questions. So it's an open question of exactly what load forecasting approach we'll be taking, but we're really excited to be able to think more in that space. So now I want to take a little bit of time and explain how we do bottom-up load modeling in the DS Grid project. Just want to do this because it might be of interest to see how you can build up an understanding of electrical load by looking at each of the different components. And also, a lot of the techniques that we use could be used piecemeal to just understand specific key drivers that you see coming in your electrical systems. So the first effort that we undertook was to see if we could model a historical load year at a really highly resolved way, building up electrical demand from detailed engineering models for the whole contiguous United States. And we're basically just wondering, could we do this? And if we did it, how accurate might our results be? And so this is a snapshot of what 4 different representative weeks looked like when we finished that effort. The area plots are showing different sector loads using different colors, and then they stack up to be our overall bottom-up representation of electrical load. And then we can visually compare that to our historical data, which is represented as the black solid and dashed lines, where the dashed line is the historical system load, and the solid line is the historical system load plus our estimate of how much electricity was generated behind the meter by things like distributed PV or combined heat and power plants. So what we can see here is that this initial effort at bottom-up load modeling was able to capture the seasonality that we see in the load, and it also captures some of the differences between weekday and weekend load. But we can also see that there are still some calibration issues. Our weekend load is often too low, especially in the peak season, which for the US is in the summer months. And we also see that there's too much swing from there's too much swing in our bottom-up representation from the middle of the day to nighttime as compared to what we see historically. Another way to look at how well our bottom-up modeling was able to represent historical data is by looking at these model fit statistics, where a model fit statistic of 1 means that we're matching the top-down data exactly, and the farther the lower our number is, the worse we're matching. And so we can see that in this initial effort, if we looked at annual load values at the census region level, which is just a few data points for the whole United States, then our estimate of load is within 5%. But if we look at it at higher resolution in any direction, we lose some of this fit. So if we break up our data more geographically or temporally, or if we look at the different sectors, then our level of fit decreases. And we can also see which sector models seem to be representing load best. And we see that in our case, our residential model is best calibrated, which is unsurprising because it's the most mature detailed sectoral model that we have. The way we put together this bottom-up picture of load is by combining a lot of different models and data sets, which are generally depicted here. The primary sectoral models are shown here at the bottom of the grid. They're called Restock, Comstock, iGate-E, and Sarah EVI Pro. Those detailed models produced hourly data broken out by subsector and end use for each county in the contiguous United States. There's about 3,000 counties. But those models don't cover all of the electrical load, and so we needed to fill in some gaps. So there's, at that time, there were some aspects of the residential building stock that weren't represented in Restock. So we have a coarser resolution description of those buildings. Same for commercial and industrial, and even transportation. Some other key uses of electricity that weren't represented in any of those pieces are the water that's used to provide water. There's a good bit of electricity that's used to both supply water, both treatment and pumping, and also wastewater treatment. And then there's a small amount of electricity that's used for outdoor lighting that's not associated with a building, but is more associated with a city, someone providing street lights. So those are all the components of our demand model. Because we were comparing our bottom-up representation to historic data, we also had that historic data that's really looking at representing the electricity sector, how much load was actually served. And for that, we have both hourly load data everything added up all together. That's that top ISO FERC 714 system generation data. And then we also have data that's gathered by surveying utilities, and that data is able to provide annual electricity demand by sector. So we have an annual number of gigawatt hours or terawatt hours used by residential, commercial, industrial, and transport customers. So both of those pieces of data are really helpful for seeing how well we're doing with our bottom-up load modeling. But to bridge the gap between those two, we also need to understand how much distributed generation there was in that historical year. So we also have a representation of that, and we really were focusing on contributions from distributed photovoltaics and combined heat and power. So I mentioned that the most mature sector model that we use in DS-Grid is Restock. So I want to give a little bit of an overview of how that works. So Restock basically provides a detailed picture of the residential building stock in the United States. At the time of this first DS-Grid effort, Restock was really focused on single-family homes, and but it's since been expanded to also represent multifamily homes. And it does that in a very granular way, providing a lot of detail that's built up from statistical sampling of different aspects of the building stock. And you can kind of see that in the picture in the background here. On the left, you can see different sample buildings in Restock and what some of their different characteristics are. And then on the right, you can see those detailed energy use results mapped out geospatially. The way Restock is able to provide such high resolution modeling of the residential building stock is by combining a lot of different data sets into a single software framework that is statistically sampled. So there's basically 4 different types of data that are integrated into the framework. First, Restock needs to understand building characteristics such as house size and fuel types used, what kind of appliances and technologies are in people's homes. So they build that up using energy code information, a survey that's conducted by the USAID about every 5 years, and other kinds of information like home builder surveys. So they start there, and then a key resource is for doing the geographic specificity is the American Community Survey, which is conducted on a pretty regularly by the U.S. Census, and it's able to say how many residential buildings there are at a pretty fine level of geographic specificity. And so that really lets Restock provide that high geospatial resolution. Then they layer on some cost information that helps provide more outputs on not just energy use, but also energy costs. And then finally, to simulate building energy use, because heating and cooling are big loads, we need to understand the climate data and the weather data. Recently, the DS Grid modeling team finished up doing load modeling work for the LA100 study, which is a study that NREL is doing for the city of Los Angeles. And I just wanted to highlight here, again, focusing on residential modeling and Restock, that this kind of second time around for DS Grid, we were much more focused on calibration and getting our calibration right for a base year before projecting electricity demand out into the future. And so what we can see here on the right is the ability of the Restock model to be calibrated to historical demand at this city level, and calibrated at not just the annual level, but also capturing monthly energy demand, daily energy demand, and hourly energy demand. And we basically did this for all of the sectors with some special focus on residential and commercial buildings, since those are historically the biggest electricity users in the city of Los Angeles. And that gave us a solid basis for creating projections, which are kind of summarized here. We had 3 different projections for the LA100 study, moderate, high, and stress. And we could see that doing this bottom-up load modeling let us capture changes in load shape starting from that baseline year and projecting out. And we can also see that the different assumptions made in these different projections really had an impact on both load quantity and timing. So we can see that both, the overall amount of demand is changing, the peak demands are changing, and the timing of when the peak demand is happening is changing, depending on our scenario assumptions. So now I just want to step back a moment. While we can do really detailed, high-resolution, statistically representative modeling of a whole building stock, we can also get insights just by coming back to the basic modeling tools, and instead of trying to understand all the different heterogeneity in a given region or things like that, we can use these tools in a more stripped down way just to understand some basic relationships, like how much electricity I could expect a home to use for air conditioning in a given locale, and how much that might change depending on how efficient the technology is that I select. And we could certainly take some more averaged kind of results like that and combine that with historical load data to get some insights into how load might change over time. Kind of thinking critically about the work we did in Los Angeles, we saw that a lot of the load shape change seemed to be driven by electric vehicles, and so we might have been able to get a decent amount of the answer there by taking a closer look at electric vehicles and modeling the other loads in a much coarser, rougher kind of way. There's definitely a lot of insights to be gained by just thinking critically about what the big drivers of change might be in your particular situation, and doing a little bit of work to understand those better, as opposed to trying to get every little detail right the first time. NREL also models load flexibility and analyzes to what extent it could help integrate variable renewables. And I just mentioned this because this is being able to do this kind of analysis is a key benefit of taking a more detailed bottom-up approach to load modeling. By knowing how your load divides up into sectors, subsectors, and end uses, you can think through which of those components might be able to be operated flexibly to help balance the system by either shifting energy use and time or just reducing peak loads. So an example analysis that we've done is we looked at how marginal PV value declines as penetration increases, as well as the ability of flexibility to preserve that value. We did this study using a production cost model of the Florida power system, and we used that to look at a wide range of solar penetrations as well as some different flexibility options. We looked at demand flexibility, but we also looked at battery energy storage and operational flexibility. One of our findings, for example, related to the demand flexibility was that our most aggressive demand response assumptions had an impact on preserving solar PV value that was similar to what we saw when we put 1 gigawatt of battery energy storage throughout the system. Associated with that same study, we also found that flexibility from different end uses provides very different amounts of curtailment reduction. So for example, residential hot water, which is a key end use in all seasons, and it has some diurnal variability, but not as much as some other end uses. It showed a much better ability of reducing curtailments as compared to residential cooling and heating, which are very seasonal. They're because they're only needed during either heating or cooling season, they can only reduce curtailments at those times, and that makes them less effective at providing that particular grid service. I just want to wrap up now with a few key points. First, if you're not doing it already, then I would definitely recommend using hourly historical load data that's time synchronized with your wind and solar profiles to do your future grid planning. This is especially important if you are looking to integrate more wind and solar resources. It can be really important to see relative to your load when those resources are going to be abundant and when maybe they'll be lacking, and you'll need to bring other resources or strategies to bear. If you do take that approach, and if you are looking out 5, 10, 20 years into the future, then you'll also want to come up with an estimate of annual growth in electricity use. You can do that by projecting historic trends, or you could also use a tool like LEAP or Made2 to help you come up with those estimates. If you want to go further, then you'll probably want to tease out different components of load. You might want to break your load down by sector. In some cases, you might want to look at subsectors or end uses. And I just want to emphasize that you don't have to do all of that at once. You could get some key insights by taking a closer look at end uses that you expect to be changing in the near future. So if you're thinking there's going to be a lot more electric vehicles, or there's going to be more uptake of air conditioning, or if there's a key industry that is a lot of your demand, then you might want to take a closer look at those things, and you might want to make a few different scenarios at how those loads might change into the future, and that might give you a better estimate of how loads might look. And if you do that scenario bracketing, then you can get kind of a range of looks and be a little more prepared for the range of possibilities that you could be seeing. And then finally, I just want to mention that demand flexibility is a potentially interesting source of grid services, and especially as we look at power systems with higher penetrations of renewable energy, those do put more of a premium on flexibility in general. And if you do think that there's key demand end uses that might be able to provide some of that flexibility, that could be another driver for taking a closer look and doing some more detailed modeling, especially for those end uses that you might be able to operate flexibly using controls and communications technologies. So that's what I wanted to let you all know about. I'm just highlighting here these really key first steps that you could think about taking that don't necessarily require a whole lot of data or really sophisticated tools. But I guess watch out if you do some of that and it's you learn a lot and it's fun, you might end up looking for a lot more data and just getting a lot of different folks involved. What I found doing load modeling work is that you know, I need to talk to and work with a lot of different folks. It's very cross-disciplinary. It's a lot of fun. So just encourage you to think more about your electrical load and what it's composed of, what it might be able to do for the grid, and also how it might be changing into the future. So thank you.